Good afternoon, everyone. I hope that you're having a great week and everybody's doing fine today. We are done with chapter 10. We have one more chapter left to go, and this is chapter 11 that we're going to be starting today. Chapter 11 takes a purely mathematical approach. We're not really looking at any true meaning behind anti-differentiating in this chapter. The one application we've looked at is that an antiderivative can represent area, but what we're going to learn today is even though area can be found with an antiderivative, not all antiderivatives necessarily mean area. So we're going to be looking today at something called definite integrals and something called indefinite integrals. And this lesson can be found on page 14 of your current lesson handout. To begin with here, just a reminder, we've seen that if you take the antiderivative of a function at b minus the antiderivative of a function at a, you will be finding the area between that function and the x-axis if the function was positive in that interval, which means if the function was above the x-axis, and if the function was continuous. However, that notation, the integral from a to b of f of x dx, does not have to represent an area. And it turns out that that equation, which is a statement in calculus called the fundamental theorem of calculus, is always a true statement whether it represents an area or not. So the fundamental theorem of calculus says the integral from a to b of f of x dx can always be found by taking the antiderivative of f of x and evaluating it at b minus the antiderivative evaluated at a. So even though we've been using this for area, you need to now broaden your horizons and understand that this integral, the integral from a to b of f of x dx, may represent something else. It might represent a net loss of money in an economics application in post-secondary. It might represent an average net force in a physics course. And those things, money and force, can be positive or negative. So I just want you to know moving forward that sometimes these integrals are negative. They shouldn't be if you're finding an area, but not all integrals are finding area. Now we're going to go over a couple of definitions and some properties of integrals. First of all, this statement, the integral of f of x dx, is from now on referred to as what's called an indefinite integral of the function. And basically what it's equal to is the antiderivative of the function. We've talked about this before when I've told you that this symbol, in conjunction with the dx, is simply giving you a set of instructions, and the instructions are anti-differentiate the function. So the integral of f of x dx is called the indefinite integral of the function, and it happens to be the antiderivative of the function. Number two, the integral from a to b of f of x dx is called the definite integral of the function. And again, it's equal to the antiderivative at b minus the antiderivative at a. So essentially, when you find a definite integral, you are evaluating the integral and you get a value for it, a number. When you are asked to determine an indefinite integral, what you're coming up with is a general expression for an antiderivative. Let's talk about property 3. All property 3 says, and we used it the other day, I believe, is that instead of integrating a constant multiplied by a function, you can always factor that constant out. I want to just correct something though. I know the other day when I factored out a -1 out of an integral, I remember saying that you were always allowed to factor something out of an integrand before you integrate. I just want to make sure that you understand what I meant to say was you can always factor a constant out. Property number 4 simply says if you want to find an integral of the sum of two functions, you can instead find the integral of the first function and add the integral of the second function. Given that functions can be negative, when we say the integral of f of x plus g of x dx is the integral of f of x dx plus the integral of g of x dx, that could be a minus as well. It could be f of x minus g of x if g of x was negative. Properties 3 and 4 are also true for definite integrals. The reason why we're going through all of this, even though it may not seem necessary for what we're going to be doing today, is that these properties, particularly the statements listed as 3 and 4, are going to be very useful for later on in this chapter when we look at different techniques of integration, which is another way of saying anti-differentiation. We're going to have to refer to properties 3 and 4 to make our jobs easier later on. All right, so let's take a look at some examples. Number 1 says find the general indefinite integral. So really the only thing that's new here, everybody, is the fact that we have this terminology, general indefinite integral. And all that means is antiderivative. So we have to anti-differentiate the function that is listed as the integrand. The antiderivative of 6x cubed is going to be 6x to the 4 divided by 4. We increase the exponent by 1 and divide by the new exponent, minus the antiderivative of secant squared. So what is it we differentiate to get secant squared? It's tangent of x, plus the antiderivative of 3e to the 2x. Well, when you differentiate 3e to the 2x, you get 3e to the 2x multiplied by 2. So we have to do the opposite here and divide by 2. And then we have the antiderivative of a constant, which is pi, and that will give you pi x plus our arbitrary constant. So because this is not an area, or because we're not evaluating this antiderivative in two places and subtracting the two values, we have to include the constant now again. I guess what we can do is just simplify this a little bit by writing 3x to the 4 over 2 minus tan x plus 3 halves e to the 2x plus pi x plus our constant. And remember, if that is right, when you differentiate the answer that we got, you have to get back to the integrand. And we can certainly check that. You differentiate 3x to the 4 over 2, it will give you 12x cubed over 2, which is 6x cubed. That's correct. Minus the derivative of tan is secant squared. That's correct. Plus the derivative of 3 halves e to the 2x would be 3 halves e to the 2x times 2, which gives you 3e to the 2x, also correct. Plus the derivative of pi x, which is pi, and the derivative of our constant c is 0, so this is our answer. It's correct. Let's take a peek at B. B is an interesting question because there are multiple different answers that you could get. The first thing I would do is I would move that constant multiple of 3 out in front so that when I ask myself how to anti-differentiate this function, the 3 is not getting in the way. Now it turns out that there are at least three different ways that you can think of this to anti-differentiate it. One of the things you can do is go to an identity sheet and say that since sine of 2x is 2 sine x cos x, sine x cos x, which is our integrand in the question, would be 1/2 sine of 2x. So I'm going to do a substitution in here and change that sine x cos x to 1/2 sine of 2x. What I am saying is that sine x cos x is the exact same thing as 1/2 multiplied by sine of 2x because of the identity that you see in the top right corner of your screen. Now I'm going to move that factor or that constant multiple of 1/2 out in front. Moving any coefficient that's a constant coefficient, that is a numerical coefficient, out in front of the integration sign makes your job easier. Because when you anti-differentiate, what you're always doing is you're always only looking at the integrand. We don't need to be confused by the 3/2. We are anti-differentiating now sine of 2x. So now I have my 3/2. I mean, I don't have to worry about the 3/2 when I'm anti-differentiating, but it's still part of my answer. And I say, what do I differentiate to get sine of 2x? Well, I have to differentiate negative cosine of 2x to get sine of 2x. And the reason is that the derivative of cosine gives you negative sine. That means I have to differentiate negative cosine to get positive sine. And I need a 2x there because the argument is 2x. The only problem is if I were to differentiate negative cosine of 2x, I do get positive sine of 2x, but I also get times 2 because of the chain rule. And that means that I need to multiply this by 1/2. I'm going to throw in my constant now. Let's just double check something. What we're getting here is 3/4, and it is negative cos of 2x plus a constant. All right, now if this is the answer, then when we differentiate it, we have to get the original integrand because we were anti-differentiating the integrand. So we can check that. This is just a check. It's not part of what we're required to do. The derivative with respect to x of negative 3/4 cosine of 2x, if you want to be really thorough, plus your constant, will be equal to negative 3/4 multiplied by the derivative of cos of 2x, which is negative sine of 2x, multiplied by the derivative of the argument 2x, which is 2, gives me 3/2 sine of 2x. By the way, the derivative of the constant is 0, so I guess I could have put plus 0 here. Now, on your formula sheet, sine of 2x is 2 sine x cos x. So I can put, instead of 3/2 sine of 2x, I can put 3/2 multiplied by 2 sine x cos x, and that gives me 3 sine x cos x because the 2's cancel. And if we go back to the beginning and look at the integrand is 3 sine x cos x. So negative 3/4 multiplied by cosine of 2x plus a constant is one answer to this question. Now, it's not the only answer. I told you that there are at least 3 ways to approach this. And I'll be honest with you, this is not what I would have done. I wouldn't have used an identity. I would have done something different that requires a little bit of weird thinking. So let me rewrite the integral that we were after. I'm going to move the 3 out regardless of the method. and I have sine x cos x dx. Now, not everybody is going to pick up on this right away, but I want you to give it a shot. I want you to try to visualize what's going on and why this works. I am going to say that the answer is 3 multiplied by 1/2 sine squared of x plus a constant. Now, why is this going to work? Well, let me clean it up a little bit. 3/2 sine squared of x plus c. What I would ask you, if we were in class together, I would ask everybody to look at that. And I would ask everybody to see if you could figure out why this is the answer. And I'm asking you to figure out why, when you differentiate this, which I'm claiming is the answer, why, when you differentiate this, does it give you 3 sine x cos x? But I'm asking you to just be honest with yourself here and pause the video and give it some thought. The answer is that if I differentiate 3/2 multiplied by the sine squared of x, which is sine of x quantity squared, I guess to be fair, plus my constant, I'm going to get the derivative here by wrapping this exponent of 2 around the base. My new coefficient will be 3. The base stays the same, and now it's to the 1. And I then multiply by the derivative of the base, or the argument, which is sine of x, and the derivative of sine of x is cosine of x, plus the derivative of my constant is 0. I get 3 sine x cos x. Which means that this is also an answer. Which is a very strange thing, because the answer we got before, I believe, was -3/4 cos of 2x. I guess I'd better include plus c. And if you take a look at 3/2 sine squared of x and you compare it to -3/4 cos of 2x, they are not equal. They are different. By the way, instead of saying it is what I have highlighted here, you could also say that this is equal to -3/2 cos squared of x plus a constant. Because if you differentiate this, you wrap that 2 around cosine, the coefficient is going to become -3. Then you drop 1 from the exponent, so you're going to still have cosine to the 1. And then you multiply by the derivative of cosine, which is negative sine. And that's going to end up giving you 3 sine x cos x when all is said and done. And I guess what I would tell you is this integral, the integral of 3 sine x cos x dx, could be equal to any one of these 3. And the reason why these are all acceptable, and you can check it out with a graphing calculator, is these constants end up being different things. If you graph these 3 functions, you will discover that they are all identical in shape, except that they are vertically translated compared to each other. And if we were in class, I would do this and I would show you the 3 graphs. But the bottom line is they're all the same answer because they all have different constants being added at the end, which means they all have the same derivative. All right, question 2 says evaluate each definite integral. You know, again, it's the terminology that's new here. If I gave this to you a couple of days ago, you should probably be able to figure it out. Be aware, though, this does not necessarily represent an area. So what we have to do is anti-differentiate 3x squared minus root 3x minus 10. The antiderivative of 3x squared is x cubed. So what is the antiderivative of the square root of 3x? I would prefer to think of the square root of 3x as the square root of 3 multiplied by x to the half. So what I'm doing here off on the side is I'm just running this through my mind and on scrap paper to be sure that what I put for the antiderivative over here of the antiderivative of root 3x is right. I can move that root 3 out in front of the integration operation. That's one of the properties of integrals. And then I have the antiderivative of x to the half, or the integral of x to the half dx. See, this to me is easier on my brain than anti-differentiating the square root of 3x. I know that when I anti-differentiate x to an exponent, the exponent increases by 1, and I must multiply by the reciprocal of that exponent, because when I move that exponent down in differentiating, I have to have something that will cancel with it. Now, I also still have my root 3 in front. This is why moving a constant coefficient out in front will make your life a little bit easier. We've determined that the antiderivative of the square root of 3x is 2 root 3 over 3 multiplied by x to the 3 halves. Then I have minus the antiderivative of 10, which is 10x, and I am evaluating that entire antiderivative from 4 to 16. So I have to put 16 in. I'm going to have 16 cubed minus 2 root 3 over 3 multiplied by 16 to the 3 halves minus 10 multiplied by 16. Then I am going to have to subtract that entire expression again, but this time instead of putting 16 in, I'm going to put 4 in. So I will have 4 cubed minus 2 root 3 over 3 multiplied by 4 to the 3 halves, and then minus 10 multiplied by 4. All right, so now we're going to start chipping away at this. And I'm going to worry right now about this piece. Part of that piece of my answer is 16 cubed minus 10 times 16. So I'm going to calculate what that is. 16 cubed minus 10 times 16 is 3936. So I have 3,936, and then I have minus this other term which I've left out of it. And the reason I've left it out is because that other term in what I have highlighted contains a radical of root 3. I want to, of course, always work with exact values. So when I look at that middle term, I can figure out what 16 to the 3 halves is. It's going to be 64. And the reason I knew it was going to be 64 is 16 to the 3 halves means take the square root of 16, which would give you 4, and then cube it. 4 cubed is 64. I also have multiplied by 2 and divided by 3, which as a fraction is 1/28. So this middle term that I didn't include is minus 128 root 3 over 3. Now I'm going to do the same thing with the second part. So I'm going to highlight the second part now. What I'm talking about calculating now is this piece. So I'm going to do the same kind of thing. I'm going to take 4 cubed minus 4 times 10. Could probably do that in my head, but just to be sure. When I take 4 cubed minus 10 times 4, or 4 times 10, I get 24. So I have a 24 in here, and then I have minus the 2 over the 3 times the 4 to the 3 halves. I'm going to do the same thing I did with the 2 over the 3 multiplied by the 16 to the 3 halves. So I'm leaving the root 3 out of it. Well, 4 to the 3 halves is 8, but I can show that to you. The reason why 4 to the 3 halves is 8 is 4 to the 3 halves means take the square root of 4. Well, the square root of 4 is 2. Cube it to get 8. Now I have to multiply that by 2 and divide by 3 as a fraction. It is 16 thirds. So I also have in here minus 16 thirds, and there's a root 3. So 16 root 3 over 3. And I guess with this question, it demonstrates to you that it's not always just about throwing numbers into your calculator and getting an answer. Our numbers here contain irrational values, root 3. So if you want to maintain the exact value of your answer, which you always do, you have to include that as part of what you write down, not what you calculate. What I end up with here is, I'll just rewrite this a little bit, 39/36 minus 24, and then I have negative 128 root 3 over 3's minus a negative 16 root 3 over 3's. So I have distributed this negative into that binomial. And I've also taken the liberty of shuffling the terms around, and instead of writing 128 root 3 over 3, I've written 128 root 3 over 3. What does this give us? Well, 39/36 minus 24 is 3912. Then I have negative 128 root 3 over 3's plus 16 root 3 over 3's. Well, negative 128 plus 16 is negative 112. Root 3 over 3's. And I just want to check that. It's been a very long day for me mentally. I better just make sure. Yes. So this is our answer. And we're not going to, everybody, say it's square units, because we don't know that this represents area. It's just a number. I suppose we can write a decimal approximation to see what this is approximately equal to. 3912 minus 112 root 3 divided by 3 gives me 3847.33677. Now there is a way to check your answer here. What we can do is put this integrand into our calculator and find the integral on our calculator. It may not represent an area because some of this function may be above the x-axis and some of it may be below the x-axis. But the number it gets will be correct. Let me show you. We have 3x squared minus the square root of 3x, and then we have minus 10. I have no idea what this function looks like. If I go zoom 6, I'm not even sure I'll be able to see the function. Well, there's part of it. Now I want to go from 4 to 16. Well, that means that I'm going to have to change my window setting to go up to at least 16. I'm going to go up to 20. And it doesn't matter that I don't see the function. If I go to my calculate menu and choose the integral and choose 4 as a lower limit and 16 as an upper limit, now it turns out that in this particular case, the function was entirely above the x-axis, so it does represent an area, but it didn't have to. The point is, if you look at the number we get, 3847.3368, and you compare that to the number we got, 3847.3368, it's the correct answer. This calculator is still gold in terms of its ability to check the value that you get. And even if some of this function was below the x-axis and some was above, the answer you get should match when you try this on your calculator. All right, in the final example, what you're going to have to do here is rewrite this integral as s squared over s minus s to the half over s plus 3 over s ds. Because the integrand before you do that is a rational expression, and you don't have a method for anti-differentiating a rational expression. You can only anti-differentiate, I shouldn't call them polynomial terms, but let me continue here and then I'll explain what I mean. S squared over s to the 1 is s. S to the half over s to the 1 is s to the negative half. And then 3 over s we're just going to leave alone. You know how to anti-differentiate each of these three terms. For the first two terms, as I said, they're not really polynomial terms. Well, the first one is, but the second one isn't because it has a negative and a fractional exponent. But you know how to anti-differentiate these. When you have a variable in the base and an exponent is a constant, the antiderivative is found by increasing the exponent by 1 and dividing by the new exponent. You have a rule for that. But what I'm getting at is you do not have a rule for anti-differentiating something like this. There's no way to do it. So we have to break this apart. Okay, so let's start anti-differentiating now. The antiderivative of s to the 1 would be 1/2 s squared. The antiderivative of s to the negative half, we have to increase the exponent by 1 and divide by the new exponent. In other words, we have to put a 2 here because when we differentiate it now to check our work, when I swing that half down in front, it will cancel with the 2, giving me a coefficient of 1, which is what I want. I didn't do anything with the 3 over s because we have a special case for anti-differentiating 3 over a variable, and it's 3 ln s. I see that I've made a mistake up here and I wrote dx, everybody. That should be ds. This whole thing is now going to be evaluated from 1 to 2. So we'll just double check our work here. Is the derivative of 1/2 s squared the same as s? Yes. Is the derivative of 2s to the half the same as 1s to the negative half? When we differentiate 2s to the half, we indeed get 1s to the negative half. Is the derivative of ln of s 1 over s? Yes. So the derivative of 3 ln s is 3 over s. It looks good. Now what we have to do is evaluate this. So we will have 1/2 multiplied by 2 squared minus 2 root 2 plus 3 ln 2. Then we are going to have to subtract the same expression with 1 in. So we will have 1/2 times 1 squared minus 2 root 1 plus 3 ln 1. Okay, what do we have here? This is 2. 2 squared is 4 times 1/2 is 2. Minus, well, there's nothing we can do with this term. It's 2 root 2. And you could put it into your calculator, but then it's no longer equal to 2 root 2 because it's going to be a decimal approximation. This, there's nothing we can do with it for the same basic reason. I suppose you could swing that coefficient up and write it as ln of 8, because you could write it as ln of 2 cubed. I don't know. I'm just going to leave it as 3 ln 2. Then we have minus, this term is 1/2. Then we have minus a negative, and this is 2. Then we have plus 0, because the natural logarithm of 1 is 0. So putting this together, I suppose we can start adding some terms together. We have a 2 plus a 2 minus a half. That's 4 minus a half, or 3 halves, or 7 halves. So that's taking care of the 2, the negative a half, and the 2. Then we have minus 2 root 2 and plus 3 ln 2. Let's figure out what this is approximately equal to, just so we can check it on our calculator. All right, an approximate number, that's 7 divided by 2 minus 2 root 2, and then plus 3 ln 2. This definite integral is approximately equal to 2.75101. If I wanted to check it on my calculator, I would have to go back up, and I'm going to graph the original integrand. I'm not going to graph what we simplified it to be. And of course, I have to use x. It was x squared minus root x plus 3 divided by x. I'm going to choose to go zoom 6. No idea what this is going to look like. That's an interesting graph. Now I'm going to evaluate the integral from 1 to 2. And I get 2.751014. That was the same number we got when we calculated it. So the answer is right. And again, even though we could say it does represent an area, we don't want to put units on it, because this function could be a function dealing with money, or it could be a function dealing with impulse in physics, or it could be a function dealing with work and energy, or charge, or a reaction rate in a chemical reaction. There are all kinds of different things that this number could represent. It doesn't have to be area. I guess what this lesson boils down to, everybody, is you getting lots of practice with anti-differentiating functions, and also with evaluating antiderivatives at 2 different locations and subtracting them. On page 505, there are a number of different questions that you can practice, 1 and 2. Over the coming days, and we don't have very many left, what we are going to be focusing on are called techniques of integration. How is it that you can look at an integrand and figure out which technique will get you the answer? And then once you've identified the technique, how do you use that technique? And notice that when I'm talking here about integration, I use the word technique and I don't use the word rule. There's no product rule or quotient rule. There are no real sets of rules for integration. There are techniques and strategies, and that's what we're going to be focusing on starting next time. I hope that made sense, and I hope you have success with these problems, and we will talk to you soon. Take care.